For the perceptual architecture of new energy intelligent driving systems, should it be a pure vision solution or a multi-sensor fusion solution with LiDAR and radar? LiDAR emits laser pulses at 905 or 1550 nanometers, measuring the time of flight to calculate distance. Mechanical LiDAR achieves 360-degree scanning by rotating a mirror. Solid-state LiDAR achieves beam steering through optical phased arrays or microelectromechanical systems. It generates a point cloud map of the surrounding environment. While this active detection method can provide accurate radial distance measurements, the information it provides is essentially not rich enough. Point cloud data lacks detailed clues about texture and color. A box shape formed by a LiDAR point cloud could be a truck's cargo bed, or it could be a billboard, or even a trash can. Its essential identity still needs to rely on the fusion of visual information. Furthermore, LiDAR has significant physical limitations. Its wavelength is susceptible to scattering and absorption by atmospheric particles such as rain, snow, fog, and dust. In bad weather, its performance will decline sharply. The reliability of its mechanical structure is challenged. The solid-state solution involves a trade-off between the field of view and resolution. Furthermore, multi-sensor fusion introduces significant system complexity, including time synchronization, spatial coordinate unification, and algorithmic challenges for heterogeneous data. An error in any link will be amplified across the perception chain. So, for a purely visual solution to understand the visual scheme, we must return to the source of perception, the human visual system itself. The human eye, as one of nature's most sophisticated photoreceptors, its working mechanism illustrates the adequacy and efficiency of passive visual perception. The human visual system captures photon signals through the 130 million photoreceptor cells on the retina. Relayed via the lateral geniculate nucleus, it detects edges and orientations in the primary visual cortex, enabling object recognition in the ventral pathway and spatial positioning in the dorsal pathway.
它还将负责识别物品形状位置的脑区传递信息。
这两种看法都是正确的，但现在情况发生了变。
The human eye does not actively emit any detection beams. By simply relying on passively receiving ambient light in the 380 to 750 nanometer band, it can accurately judge distance, speed, material, and intent. This biology shows that a complete understanding of the 3D world does not have to rely on active ranging technology. Just by passively receiving and analyzing reflected light in the environment is enough to support high-speed, complex navigation and decision-making. Humans navigate safely in diverse environments. By using sufficiently advanced algorithms to engineer a reproduction of this, it should become the most direct and scientific path to achieving autonomous driving for machines. A pure vision solution is based on visual simultaneous localization and mapping, or VSLAM technology. Through feature point extraction, optical flow analysis, and motion structure recovery, it can build a real-time 3D representation of the environment from a video sequence. For example, the occupancy networks used by Tesla's FSD system directly predict the occupancy probability of each voxel through neural networks, forming a continuous 3D scene understanding. Traditional monocular depth estimation relies on geometric priors, but deep learning-based estimation trained on large datasets achieves over 98% relative accuracy for depth prediction. Via CNN and VIT architectures, the system extracts multi-scale features from a single frame and binds semantic context to infer depth. The core advantage of pure vision solutions lies in the use of temporal information. Through time series modeling with RNN or transformer, the system can integrate the motion information of successive frames, forming a 3D space plus time dimension. This dynamic modeling capability allows for the accurate prediction of an object's motion trajectory using only vision. There's no need to rely on radar's Doppler effect for speed measurement. And here's the thing. Visual information is extremely rich. It identifies where objects are, what kind they are, surface materials, and their state. This high-level information is essential to predicting behavior, understanding right-of-way, and processing the scene. So, for scientific logic and work efficiency, the pure vision scheme has clear superiority. It follows the principle of highest data efficiency and cognitive consistency. The camera captures the data stream with the highest information density at a very low cost. This provides the best training for a data-driven autonomous driving system. In fact, when human pilots are dealing with driving tasks, the brain integrates multi-sensory information, but vision has always been dominant. When touch feels a vibration or hearing receives a message that conflicts with visual judgment, we humans instinctively believe in sight. Autonomous driving system design should also pursue this kind of cognitive consistency, avoiding conflicts due to sensors that lead to decreased credibility of decision-making systems. On the path of extensibility and evolution, the pure visual scheme is equally clear. Performance improvement is directly linked to the ability of neural network models, the scale of computing power, and the quality and quantity of training data. These elements all follow a clear law of exponential growth, while the performance improvement of LiDAR is more constrained by the laws of physics and manufacturing costs. Of course, the core difficulty faced by pure vision solutions is how to overcome the accuracy issues in extreme low light conditions or in cases of visual obstruction. However, this is precisely the area where cutting-edge research is making breakthroughs. By introducing more spectral perception, physics model-guided neural network denoising, and hyperscale real-world data-driven domain adaptation training, the all-weather capability of the visual system is rapidly approaching and surpassing multi-sensor systems. Advanced pure vision systems, through predictive modeling, are able to penetrate rain and mist and imagine the outline of an obscured object. Or, under strong backlight, it can infer and restore road information from before and after information. This is no longer just simple image processing, but an embodiment of a deep understanding of the physical world trained on massive amounts of data. So what do you think? Should we learn from Tesla and stick to the visual plan?